So for those of you who don't know what the MWA is, or the Murchison Wide Field Array, we're moving to the radio regime now. The MWA is a low-frequency radio telescope, so it operates between 50 and 300 megahertz, and it's located in the Murchison region of Western Australia, very close. It's about 10 kilometres from where the square kilometre array low-frequency component will be built. So this is a photo of some of the tiles. So the MWA currently consists of, well, there are 256 of these individual tiles. Each of these little 16 sets of dipoles are beam formed together to have one view of the sky, and then we cross-correlate each of these tiles together to form an interferometer. The array is currently working, and it currently has 136 tiles that can be operated at any one time. So these are the MWA EOR members as they stand at the moment. We've had a couple of people move on as they've graduated their PhDs, but we also have a couple of new members I'll just highlight for you. So Karaoke, you just saw Karaoke. This is his first time he's actually been out of trouble, even though he's been in the program for a while. And Jaden is also here. In terms of our new members, we have Aishwarya, and Ash is in the audience down the front, so she's only a few months in. Redeemer is our new Astro 3D postdoc. And we also have Tepe, who's a new postdoc from Japan, and Dev, who is a software engineer working with us. Angel's going to steal the limelight. and thanks to Lister, we know we also have 83 collaboration papers in Astro 3D, so this is a really good number as well. Okay, so if we look at the global landscape of 21 centimetre experiments, what we're looking for here is the reionisation of hydrogen in the early universe. So early in the universe, the universe is filled with neutral hydrogen gas, and we know as the first stars and galaxies turn on, and their stellar remnants really of them have photons that are hard enough to actually be able to reionise that hydrogen and see the universe that we see today, where neutral hydrogen really exists in shielded regions in galaxies alone. And it's this signature of reionisation that we're looking for by tracing the evolution of the 21 centimetre hyperfine line of hydrogen. So there are a lot of experiments around the world. They're mostly located in places that are radio quiet. 50 to 300 megahertz sits right within the FM band of radio, and a number of other interfering radio frequencies. And so we try and put these a long way away from people. So remote Western Australia is a really excellent place for the MWA. ASCAP is also there, the Future SKA, and a few other experiments as well. In terms of the field that we're looking at, which is the interferometric experiment, where we're trying to understand the spatial distribution of hydrogen on the sky as a function of redshift, it's really that the MWA, Hera, which is an array in South Africa, and LOFAR, which is the Dutch array based in the Netherlands, and they also have an EOR Key Science project. But you can see there are a lot of other telescopes around the world that are pursuing this in some key way. So these slides very much overlap with the ones I showed in December last year, but with a few key differences. So these are the redshift ranges we typically look at when we're looking at reionisation. So this is a typical model of the evolution of the brightness temperature of hydrogen over time. So we're taking cuts through the universe and we're evolving forward in time. The colour here is showing you that brightness temperature, and there are regions of the times in the universe where we expect that to be in absorption against the CMB, and times in the universe where we expect it to be in emission in the CMB. And it's really this reionisation region here that we're mostly interested in, where the neutral hydrogen is being eaten away, and the fluctuations you see spatially are actually dominated by the ionised and the neutral regions spatially on the sky, rather than any other factor. The new thing that I will talk about is the Cyrus 3 experiment, which is an experiment to look at the evolution of the global signal, which is what you can see on the bottom there, after the very famous EDGES result from 2018. So in terms of the work that we're doing, we don't have a detection yet of the statistical signal from reionisation. In fact, we don't have any detection at all because the EDGES signal is shown to not be of cosmological origin. So this is still a wide open space, and a lot of our work is to try and perform this very precision experiment to try and find this very, very weak signal with a very, very complicated telescope. And so all the work that is done by the team, and I've put some of the faces here, and this is certainly not everybody, is to really understand all of the pieces of the puzzle as the signal passes from us through all of the lower redshift galaxies in front of us, through our own galaxy, through our ionosphere, through our complicated telescope, and then through the complicated way that we do the analysis. And we need to try and spit out something at the end that is actually, we can show has cosmological origin. So this is where we stand. I showed this slide in December. This has not changed, but just to show you that a lot of these results that came out of Astro 3D are within the last year. You can see all these ones in the centre here in 2021 and the ones on the right. So what we're looking at here is the power spectrum of brightness temperature fluctuations at a particular redshift. And the green lines you can see on this particular plot are the thermal noise levels, and the detections that you can see here are in the red and the blue, and it's the same in all of the plots that you can see at the different redshifts. And the key point here is that these are not detections of the cosmological signal. These are foregrounds. These are systematics that are getting in the way of us actually seeing the signal that we're interested in, which is actually down here somewhere, we think. We're not exactly sure, but it's actually down here somewhere. This work here that we led a couple of years ago was the deepest ever publication of results of any telescope of their data. This is 110 hours of data has gone into each of these lines. This theoretically would be actually at the signal level if we could get past those systematics, but you can see we're systematics dominated. So this work is really MWA EOR work. The work on the right here is a bit more broader. These are actually not just sort of systematics limited, but actually now looking at the underlying astrophysics, so trying to measure the actual temperature of the IGM. And then on the bottom right is the work of Brad Gregg, who sits between MWA and Genesis, to actually look at what we can say about the underlying astrophysics from the limits that we have at the moment. And certainly there is something that we can say. So I'll talk a little bit more about where we're going with these results shortly. But I just wanted to highlight that LOFAR and HERA have also had results in the last 2 years. HERA results of 2021, not 2020. But that there are comparable results from the three telescopes across a range of redshifts, and we're all sort of trying to beat down some of these systematics to be able to get deeper and deeper. So the final thing I will mention, because I don't think this got highlighted very much in the media, but there was a lot of attention given to the 2018 EDGES result, which was claimed a detection of the absorption trough at 78 megahertz. This is a trough that marks the birth of the first stars in the universe and how that changes the hydrogen signal. It was a very deep trough. It was one that we found very difficult to model with our models of the early universe. So Cyrus 3 went out specifically to try to demonstrate whether the EDGES result had a cosmological origin, and they've been able to rule out that to very high significance. So what that means is it doesn't mean the EDGES result is completely wrong. It means that, that there are some systematics in it, so we need to keep working. Okay, so just quickly to highlight some results. So as I mentioned, last year we talked about the fact that we were commissioning a new system with the MWA, and that commissioning is now complete. And as of this week, the array is back up and running with 136 tiles, and we'll be starting to observe in the EOR season this year in September. And I'm hoping we'll have more than 136 tiles for that array. Okay, so I'm just going to highlight a couple of results from the students that aren't being discussed today. So Karaoke, you've just met, has been working with one of our calibration tools, the RTS, and in particular working with Bart Pindall to try to improve our understanding of the ionosphere and how we treat the systematics due to the ionosphere in our analysis. And you can see here some nice models of what the ionospheric phase screen looks like and how we then go about using that in our data. What is the best way to be able to treat that when we're actually calibrating our data to be able to perform this experiment? So he has a paper that's nearly published in that space. Mike Creel has been working on all sky maps so that we can understand what the diffuse emission component from our own galaxy looks like. And in particular, he's doing some work where he's combining data from LOFAR and from the EDA, which is basically like an oversized MWA tile, together so that we can see the whole sky at once, and we can actually map the entire diffuse emission of the sky in 24 hours by just letting the sky drift overhead the two telescopes. And so this is really important for our sky model. This is the first time this has ever been done. And Ash, who I mentioned before, she's only 3 months into her PhD, but she's going to be using this oversized MWA tile that we call the CRAN. It sits in the middle of one of the southern hexagons of the MWA, but because it's oversized, it sees the sky in a different way, and we're going to use the statistics of those measurements to be able to help us to remove the problems that we have from bright sources close to the horizon. Okay, so one thing, and this is a really ugly slide and I apologise for it, but what I want to demonstrate is where we're actually moving with this. So on the left-hand side, I'm showing you the 110 hours that we published 2 years ago. And this is the power spectrum in a two-dimensional space, and this is the one-dimensional one I showed before. And I don't have much time, but what I'm going to say is that this region here is where we want to pull out the signal. And you can see that here, it's very systematics limited. We have no negative pixels. It's not noise-like. And you can see the result we have here, which is a few by 10 to the 3 millikelvin squared. We now have a new calibration system. It's called Hyperdrive. It's doing a much better job at calibrating our data. What you're seeing on the right-hand side now is 38 minutes of data compared to 110 hours. And the results that we're getting out of it are much closer to noise-like and almost matching what we published as best slippers 2 years ago. So all of the work that's going into the calibration analysis is making a difference. And so I'm very hopeful that we're moving in the right direction. I won't show the milestones because that's boring. What I will talk about finally is where people have gone from MWA EOR. So this is a centre. Part of the job of the centre is to ensure that our people are moving on to places that they want to go. So this is roughly time ordered. These are people who were part of MWA EOR and have moved on. So you can see people have moved into faculty positions, international fellowships. Nicole's back to speak. She's now an independent forest fellow. Mike Creel hasn't even submitted his PhD yet, but he's already started his postdoc at UWA. I'm really happy to report that Christine and Karaoke, who are still working with us, are also both moving on to excellent positions. So Christine's just accepted a tenure-track position at University of North Carolina, and Karaoke will be defecting to the LOFAR EOR collaboration and going to work for the Cath Institute, which is excellent. That's really good. And I'll stop there. Thanks.